Welcome. In this video we'll learn how to really understand more the shear stress development in beams under shear forces. And up to this point we learned the shear stress formula from a shear force, and it's tau. It's a shear stress. Tau is equal to VQ over IT. And V is the shear stress. We learned how to calculate tau before from a torque, not a shear force. But in a shear force, V, the formula have also I, so the moment of inertia of the cross section. So and then Q and T. So we've seen the proof and of how we ended up with this formula. The point is here at a section, we are interested to calculate the shear stress at a point within this section. So for this section, V and I are fixed for all the points. So what makes difference related to the stress distribution over the section between different points is really Q and T. So in this video, we'll understand more the implications of Q and T, specifically Q. We want to understand what's really Q. So if we are interested to find Q here for point P, because we will be able to find tau at this point, so Q here is defined as the first moment of area of the shaded area here, or what we call here psi. Psi, this is the part that's, if I slice the beam, so the beam is like that, and if I look at the cross section, the point is somewhere here, like here. And what happens is I want to calculate the shear at this point, so I want to figure out the Q value. For the Q, I will slice this part. So I will slice this top part of the beam where P is at. And for that sliced part, psi, I will calculate its first moment of area. So I will figure out what's the area and then times the distance y bar psi. So y bar psi is the distance from that circled point in the middle of the shaded area to the neutral axis of the whole section. And that's really Q. So for any point, you figure out what is the area that's marked by this P point, or the point here, slice it, and then calculate the first moment of area of that sliced part. So let's practice here by figuring out Q for the shown 5 points in a rectangular section. And these points at the top and bottom of the beam, in the middle of the beam, and at quarter height of the beam, top and bottom. So if I look at point 1, if I try to slice this part that's at point 1, I'm actually slicing almost the area here. So the area of psi, A psi here is equal to 0, so this means that Q1 is equal to 0. If I move to the second point, which is quarter height in the section, so if you are a quarter height, the area that I'm slicing here is the top quarter of the beam. The centroid of that top quarter of the beam is in the middle between a quarter of the height and half of the height. So that will be 3/8 of the height h. And then A psi will be, again, the area times, so A psi will be the area here, so the thickness of the beam, or the width, what we used to call width, but here we call it T, it times h over 4. And then Q will be this area times the y bar, so I will end up with 3 over 32 th squared. Moving to the next point, which is at the neutral axis. So the area here that I have is half of the area of the section, th over 2, which means that Q3 will be this area times the centroid of that shaded area, or the psi area, which the centroid here is at quarter height. So it will end up with th squared over 8. Moving to point 4. Point 4 is actually similar to point 2. So it will be kind of the same case, and we'll end up with the same value for Q. And then at last, the 0.5 here is similar to 0.1. It will have 0 Q value. So you can see here that observing these 5 Q values, Q max is in the middle, is for the point that is in the neutral axis, where the area is the max and the distance here times the distance, that will give you the maximum Q. And that's typically the case in most beams, especially rectangular ones. So it's typically the maximum Q, which results in the maximum tau, will be for points at the neutral axis of the section. So if we're looking now into rectangular beams specifically, we figure out now that tau max, considering that Q and I can calculate them with the, so this is a typo here, that should be H. So H and T dimensions of the cross section. TH square over 8, that's the Q max I figured out from before. And then the moment of inertia, that's around the axis perpendicular to V. So it's not the vertical axis, I'm dealing with the horizontal axis here. So that one is TH cube over 12. If you kind of work out the math here, I will figure out that tau max is equal to 3V over 2A. Remember in the first lessons of this course, we said that tau average is equal to V over A. And now we are able, with advancing in this class, we can now really calculate the shear stress from a shear force in a rectangular cross section here to be like know exactly what's the maximum shear stress in that section, instead of just calculating an average value, which is V over A. Now I know that the maximum stress in a rectangular cross section is equal to 3V over 2A, and it happens at all the points, any point on the neutral axis of that rectangular section. So this means if I plot the distribution of shear stresses, any point, all the points with the same y coordinate will have the same tau value, and this tau value will be equal to 0 at the top and the bottom of the beam. Unlike bending stresses, it will be maximum at the top and the bottom of the beam, but for shear, it's equal to 0 at the top and the bottom of the beam. And then maximum shear stress in rectangular sections will be at the middle, or not middle, the neutral axis of the section. So let's see here, maybe a little zoom in and see what happens really, what this tau represents. So we'll zoom in at a point here. So this is the same cross section of the beam in 3D, subject to a shear force here. And I'm interested into that point, and if I'm interested into calculating the shear, then I need to slice that part and kind of see what's really happening for at this point, at a distance y from the neutral axis of the section. I will see here that I will be able to calculate tau using VQ over IT formula, and all the points at this y coordinate will have the same tau value. But from the general state of stresses, we learned that tau cannot exist alone on one surface of this 3D block of general stresses, the general state of stresses. So there will be another tau developing on other faces of the cube. But let's agree here on the coordinates, so x, y, z. Once you set up the coordinates, I can give now names to that tau stress. So tau, the first one I showed, tau in that surface in our side, or we're facing, tau is equal to tau xy. So it's tau in the surface perpendicular to the x coordinate, and it is in the y direction. Now we learned before that this tau xy cannot exist by itself, so there are other stresses developing, tau xy in the opposite face and tau yx in the perpendicular faces. So in this case here, tau yx is developing, which means there is a longitudinal shear stress developing in that beam beside the transverse shear that I calculated here. And these two shear values, tau yx and tau xy, or the longitudinal and the transverse shear, are equal. So this formula that they have been using so far, tau is equal to VQ over IT, is calculating at any point the transverse and longitudinal shear stresses at this point due to a shear force V in that beam. So that's the end of this video. We'll learn more about Q. Q is the key, similar to in bending stresses or in the shear stress from torque. So tau is equal to TC over J. J is the key word here, or the real acting factor in the case of shear stress from torque. And shear stress from V, shear force, the key factor here is really Q, VQ over IT. This Q, this moment, first moment of area of the part that you slice to analyze the stress at, this is really the key. All right, that's it for this video. I'll see you in the next video. We'll see an example of analyzing shear stresses in a beam. So that will be a numerical example. We'll do in detail the formula VQ over IT. All right. Thanks for watching and take care.